This video is recorded on 21st of October 2019. This is the class number 20 and we are going to derive the fixed end reaction of the beams under distributed loads. So today we will consider two cases. The first case is the beam under uniformly distributed load, and the second case is the beam under the linearly varying distributed load. Factor or the fixed end reaction. So let's take a look at this together. So in the presence of axial force and your structure is subjected to the span loading, so we will start from the uniformly distributed load apply on the span. Right. We'll be setting up the governing differential equation in the same way as when we derive the stability functions. So basically we have a reaction like this. We have, of course, the axial force that is applied like this, and we have the moment applied to this structure. Okay, so we have the RA, RB, we have the moment M, A, MB, right? And then we will set up the differential governing equation for this beam subjected to the applied uniform load. So we will take the cut for the equilibrium in order to set up the equilibrium equation. We will cut it, we'll use this. So the deformed shape is, well, arbitrary, okay, whatever. We have no idea where is the inflection point, where is the positive or negative curvature location, but from our assumption we should be setting up everything consistently and be able to come up with the right solution. So but that looks terrible for the beam. Okay, fine. So what do we have? We will this part here will appear on the equation on the differential governing equation, we have a new thing that comes into this place. So let me just give you all dimensions. We have this being the value of the x, this is the y, right? So this point here depends on how you want to set up the direction, but if you go this way, okay, so if we call it MQ, and we take a moment about the point Q. So summation of moment equals to 0 about point Q, and let the positive sense of the moment for this setup in the moment equilibrium be the counterclockwise. Well, if you want to set it up in a clockwise direction, it doesn't really matter, okay? It will work because this is just an equilibrium equation. There is nothing to do with the sign convention. The sign convention comes when you put things together in the direct stiffness format. But for now, if you want to say, okay, I want this to be positive, fine, just go ahead. It doesn't really bother. Well, I used to just set up in a counterclockwise direction being positive. Let's do it this way this time, okay? It doesn't hurt. So look at this together. We have the MQ. Wow, the MQ is going in a clockwise direction already. So we have the positive MQ. What else? We have the RA multiplied by X, right? RA times X. We have the minus MA, right? We have plus P. And what? P multiplied by Y. Well, we will come back and fix the sign. We will neutralize the sign here in a bit. Okay, so let's put all things in here first. RA, MA, PY, what else? W, right? W produce the counterclockwise if you refer to the point Q, right? The moment produced by W, distributed load, is going counterclockwise direction. So we have the minus W multiplied by X and then multiplied by X over 2 being the moment arm of this load effect. We look at all things. Okay, so in the next slide, let me just fix things up. I now have the Wx squared over 2 on the right hand side plus Ma minus Ra x over L, no, not over L, Rax, right? And on the left hand side I have the MQ, and basically I think I should just expand the MQ, which is just the EI. You look at the MQ, the direction of the MQ implies that the curvature is going to be negative, right? So EI, and then I neutralize the sign, so second derivative of y with respect to x. And then what? Plus the P, but the y is below the x-axis, so we need to neutralize the sign for the y, so we have the minus y. Oh, by the way, the last class video, it was not uploaded because the file was broken, So I'll find a good opportunity to fix it and upload it. Okay, so probably very soon. Oh, and by the way, just for your information, if you are interested, this Wednesday, if you walk into our structural engineering laboratory, you must see one specimen which is very mature and ready to test very soon. A bunch of strain gauges sticking out of this. We have somewhere around 150 channels of strain gauge and transducer and sensors. So this is going to be a very nice test that you can see, but it is going to be on this Wednesday. Monday I'm not available. Tuesday we're gonna have class. I cannot stick around. So Wednesday, which is the AIT holiday, then I request my student to test on that day. So you can stop by anytime. It will take time to finish the whole test process. So if you want to see the physical specimen testing of the reinforced concrete structure, all right, you're going to see, well, I use 4 load cells for this test, a bunch of displacement transducer and a bunch of strain gauge and many data loggers. All right, you're going to see a lot of equipments there. So if you have the interest in this particular area, then okay, that's a good opportunity, and it will take quite very long time, so you can stop by anytime. Probably it's gonna start in the morning, and I will take the video recording, so I'm gonna explain to the video what are all of these, and then also put on YouTube, and you can get access to watch this if you don't want to make it to the lab. All right. Up to you, because nothing is mandatory with me. But okay, let me just get out of this business on the screen just a little bit real quick. In structural engineering, you have many things to do. Well, for the research point of view, the first thing is the physical specimen testing, which is done in order to learn about the capacity, about the possible failure modes of the structures, or maybe new structure or the existing structure that you really want to learn, because structural analysis program that we use for the design, generally it cannot incorporate all the failure modes. You don't get the ductilities, the real ductilities of the structure. You change the detailing in the reinforcement, you change the ductility, you change the failure mode. Alright? So it is important to conduct physical specimen testing. So you can see that, oh, well, shear failure came in over here. Well, you can use the theory you learned in RC design. Things you have in the code like the ACI, or things you might have seen in the publications, in the paper, journals relating to structures like concrete or steel. You can predict somehow the failure mode or the ductility of a structure for general cases, or the cases that people have been thoroughly studying into it. All right, in those cases, but many cases sometimes you want to invent a new kind of structure, like precast concrete members, load-bearing walls, which is made of precast. You connect the precast using some gadgets that is new, and the new things that people are not dealing with like in a day-by-day basis. You need to test in order to be able to identify, oh, these might be the failure mode that you need to be well, giving like a very good attention on it. All right. So that is why the physical specimen testing is still required for this day. You see a lot of development in Eurocode, in ACI, in many codes around the world, Japanese, etc. You name it. But still, the code cover the area that people have explored. In very well, people get like a very good understanding in those areas. So it's become the code. But many areas that Columbus has not arrived. You need to be the Columbus to walk over there and then to make the recommendations on the new kind of structures or the detailing we have. Okay, and to learn, failure modes, ductilities, many things, capacity, and so on and so forth. So we test. That's one thing. So physical specimen testing. Other kind of things. Physical specimen testing generally it does under the very slow loading rate. This one here to be tested on this Wednesday is the test under the effects from the gravity load. This is the new precast connection I came up with. Right, so I invent this system, and then I want to show that this could be used. So I need to test it. Okay, so it is somebody thesis, and the first thing, the structure needs to withstand the gravity load effects first. All right, so this specimen is for gravity load, but in probably a few weeks or maybe about a month from now, you're gonna see another specimen which is made by exactly the same connection technique, right? But the specimen will be tested under the reverse cyclic loading, horizontal loading, so that simulate the effects from the earthquake that produce the lateral drift to your structures. This is a frame structure, so you'll be seeing another specimen which is going to be erected just very in the same vicinity, but the loading pattern, the load configuration will be different. So changing from the vertical gravity load to the horizontal load, and that's what it takes to come up with a new connection system. But first thing to test under gravity load. So you can stop by a few minutes. You want to stick around for a whole day, it's up to you. If you have time, you sit there. If you feel like this is very interesting for you, you just stick around. So we apply load, we check the damage on the structure, we check the parameters that is progressing with the load, like strain, etc. And we will try to make sure that the test will be able to get everything useful from the test. Many times the strain gauge installation, sensor installation could be done in a wrong way, and then at the end of the test you miss many strain gauges or some sensors. This one we try to make sure that we can squeeze out all the things from this specimen. Right, so it might be interesting for you if you just envision you a little bit before you came across the second semester, end of the second semester, that you need to select the research topic for your master thesis. Then you get some idea that, oh, alright, this is physical specimen testing. Oh, I don't want to do it. Oh, I like to do it. Well, that at least you know that is it what you like to do. Alright. Okay. So you are invited if you want to go and take a look. I'll reshape these equations. I come up with the second derivative of yx plus k square y equals to rax minus ma minus w effect wx square over 2. So we have the homogeneous solution again. like before. I need to expand this a little bit because our particular solution will be a little bit different from before, because you need to incorporate the wx squared term in there in the particular solution. So look at the particular solution. Our particular solution has to contain the x squared term, right? Otherwise you will not be able to have this x squared term on the right hand side. So it contains some x squared term, but let's see. So we have the cx squared plus dx plus e. Right, just be very careful. The e has nothing to do with ei. Sorry, I just drop off the ei here, right? ei and ei. Other kinds of tests that we can do is dynamic testing in the lab. Even it is reverse cyclic or the gravity load, the rate of loading is very slow, quasi-static. Okay, we call it quasi-static testing. But we can also conduct dynamic testing, generally in the real structure, in the field, like the bridge, like the building. That kind of dynamic testing, we don't bring our structure to the collapse, to the real failure. Right? In the real testing, real structure testing, we sometimes want to learn about the dynamic characteristic, like the natural frequency. You learn in dynamics. We want to figure out the damping ratio. We want to figure out the mode shapes of the structure. So that could be done in a field, and that use different kind of sensor. So generally we use the accelerometers to pick up the dynamic information. Strain gauge can be used also. Displacement transducer is not good for the dynamic properties, but dynamic, you want to learn dynamic characteristic. Just that, you don't want to learn failure mode. You don't want to learn the ductility. Okay, so that will be the different kind of testing, and the purpose of the test is different. And the other kind of research, you are living in a computer world, playing with a program like ETABS, SAPS, and so on and so forth. In order to do that, you need to be very sure, very certain about the assumption that you made. Because you use the computer program, you will not see the real phenomena. It doesn't incorporate many things. So if you want to use it, you need to address all the you need to list out all the possible assumptions you have. For example, if you want to run the nonlinear time history analysis of the building under the earthquake using ETABS, perform TDs or SAP, you need to make sure that the nonlinearities that is incorporated by the program, right, is the kind of nonlinearities that well, that is available. I mean, how to say? You cannot over conclude the result you have. So the program can incorporate something like plastic hinge formation. Okay, you need, first of all, you need to read through the manual of the program and see what is capable for the program. Okay. Plastic hinge formation or flexural kind of nonlinearities can be incorporated. Alright, fine. Is it possible to incorporate the shear failure? Yes or no? That depends on the structural elements that you use. There are many kinds of structural elements in this program. Some is capable of exhibiting some strange kind of, some difficult kind of failure, like shear failure, crushing, etc. But some type of failure might not be incorporated. For example, the bond slipping. What else? Gap opening, gap formation, Sometimes that depends on the construction detailing. So do not use the program and believe that it is going to produce exactly the same behavior as your structure. If you need to look into your structure and see if there is any possibility that other kinds of effect that the program cannot handle is going to happen in reality or not. Right? Program can handle A, B, but your real structure will exhibit A, B, C, D. So the C and D will not be incorporated in the program. And then if you use the program and you say that, oh, right, this structure is going to be okay, but the assumption is to say that C and D will not be significant, and you can just omit the effect of C and D. So, well, you need to testify that C and D is really, really negligible, right? So it is dangerous if the use of the program without knowledge, without any concern about the reality of the actual condition of the structure is really dangerous, right? Use with care. All the program, structural analysis program, has a disclaimer phrase when you open the program. It says that they will not be responsible for any problems that you made using this program, right? So as a user, you cannot just use it and believe that the program is going to give the one-stop solution for you. Right? Getting out of the screen for many times, but I think I made all the points already now. So substitute the particular solution into there and there. Differentiate twice. The dx and e will be gone. First time you get cxc or 2xc, and then the second time you're gonna get just the 2c. So that's the part that you have from second derivative of y with respect to x. And then plus k squared, or, well, that's the p over ei, right? I just put it back into p over ei terms again. We have the cx squared plus dx plus e equal to this whole thing on the right hand side. Oops! Copy and paste. Right, this whole thing. So let's take a look. The easiest one to match the x squared term and the x term will be together. Okay. So wait, this is also there with the green line. So first of all, I think the easiest one, the C, P over EI times C is equal to minus W over 2EI cancel out. That makes our C be minus W over 2P, right? How about the D? dP over EI equals to R over EI. Cancel out the EI, and then we get the D is equal to RA over P. And the last one is the combination between the C plus E. So 2C plus PE over EI equals to minus M minus M over EI. Okay, PE, alright, okay. Let me just move to the next page. We run out of space here. Paste. Don't cancel out this E and this E. So C, what is C? Minus W over 2P. So I substitute minus W over 2P multiplied by 2. So that is just minus W over P. Then we move it to that side. And then I put the EI there, P squares here, and minus turns out to be plus. WEI over P square minus MA, that EI cancel out, MA over P, and that is your E. So let us rewrite the whole thing. The solution Y is equals to A sine KX plus B cosine KX plus, how about the C? C is minus W over 2P minus W over 2P X squared, right? And the D is R over P plus RA over P multiplied by X, and then the last term plus W EI over P square minus MA over P. So here, who are the unknowns? A, B, W we have to know, right? The applied load. RA and MA. Alright? So still we don't have more unknown. And these 4 unknowns will be figured out by the enforcement of boundary condition. So let's take a look at this. We enforce the boundary conditions enforcing the boundary conditions. So the first one, y at 0 is going to be 0. So 0 is a times 0 plus b times 1 minus 0 plus 0 and plus WEI over P squared. That makes the B equals to minus WEI over P squared. First condition. Second condition. Over here we see that this beam is fixed, so you cannot use the force boundary condition, right? You have only just the displacement boundary conditions. And the second thing to use is the slope. So dy dx minus what? M over P. You mean here? I missed one thing, right? Okay, thank you. M over P. Actually, this is MA. I will just be drop off. Okay, thank you. So we get the M over P. Thank you. Yeah, I feel like, why is it so so easy? X equals to 0. The form looks not complicated at all, so but A K 1 minus B K 0, and then 2WX, well, this is going to be 0, plus RA over P. That's it. So the A is equal to minus A over PK. Number 3, substitute the L into the X. We have the A sine, well, 1 second, A, which is the minus A over PK sine KL. How about B? The term gets quite EI over P square cosine KL. And then what? WL square over 2P minus WL square over 2P, and plus RA L over P, RA L over P, plus WEI over P square, and minus M over P, MA over P. Rearrange. The WEI over P square is actually, this term is actually equivalent to W over K square P, right? Because the EI over P is equivalent to the 1 over K square, so the K square is there, and you know, leaving the K square alone is not good. The K is supposed to be with the L, so I multiply by L square up and down like that. Then that makes the WL square over P, and then 1 over KL square, right? And then you be getting this and this in a quite similar format, right? Okay, so we agree to change this to WL square over P 1 over KL square. WL square over P times 1 over KL should make it like this. Square. Okay, nice. This looks good. Yeah, everything looks good. Okay, reshape this equation just a little bit more. Basically, I should move it down by 1 level, 0. And then I regroup things. So start with the L over P. This multiply with these things inside, RAL over P, well, 1, and then minus sine KL over KL. Okay, so RA, well, we have only just 2 RA terms. Plus the M A over P. So the MA over P, the first one is cosine KL minus 1. That's all. Plus WL square over P. Actually, there's some reason behind. RAL over P, what is the unit? It is in the length scale, right? MA over P in the length scale as well. WL square over P in the length scale, right? And the thing inside the brackets are purely dimensionless because that's a function of KL, and KL is dimensionless, right? So dimensionless times the length scale, you get the length scale, and we are talking about the boundary condition for y, function of y, not derivative of y. So this makes perfect sense. At least you can check the correctness of this derivation along the way. You shouldn't get some surprise unit out there. WL square over P, right? So start with 1 over KL, we square it up, minus a half. Is there anything else? Yes. WEI over P square, that is equivalent to minus cosine KL over KL square, right? From this here, WEI over P square is equal to WL square over P multiplied by 1 over KL square. So we push the 1 over KL square to the denominator of cosine KL. We extract that out, we common factor it out. That's what we end up with. That's it. 1, 2, 3. 3 terms for W. 1, 2 terms for RA, and 2 terms for M. Okay, that looks good. Well, we're gonna have to name these terms. Alpha, beta, delta, A, B, C. C was supposed to be kappa. Kappa, or that's a K. Yeah, K, kappa. C, or theta. Fine. We are not learning Greek class later. Class number 20, page number 2, 2019, 10/21. Okay. So move to boundary condition number 4. Number 4, derivative of y with x, where x equals to L is equals to 0. And that makes the AK sine turns out to be cosine. Oh, sorry. We were not supposed to leave the A. What is the A? Minus RA over PK. A over PK, but derivative of sine, you get K cosine. K cancel out. You have cosine KL. That's the A. How about the B? The B is M over P and minus W. Okay, so plus MA over P. Okay, put the K there, then minus W EI over P square and times K. Alright, and that is the sign KL. I need to fix the sign here to be the minus, as it is the derivative of cosine. Looks good. And then we have derivative of the WX squared, that is 2WX, 2 cancel out, WL over P. So that will be just My W today is not beautiful. WL over P. WL over P minus, sorry, and then WL over P is there. RAL derivative, we get just RA over P, so plus RA over P. That's it. 0 is equal to group up. If we multiply through by L such that our equation here is going to be pretty much like the equation on line number under the condition number 3. So the dimension of this setup will be in the length scale dimension. We have the RAL over P (1) minus cosine KL. And that's the RA, and M minus MA over P multiplied by KL sine KL. Looks lovely. Plus what is it? WL square over P. WL square over P, and then in the bracket we have the sine KL over the KL square okay, and then what? Minus 1 yeah, that's it. A, B, C, D, E, eta, F, G, what is the G in Greek? H, I, J, what is the J in Greek? K, kappa, okay. Well, but the kappa looks okay, omega. Just put it this way. You have all these three things. You have equation for K in front of sine KL. You mean here? Here? Let's see. Okay. This part is a K square. Okay. K square. Okay, that's over K square. And then the P remains over K square multiplied by okay, that 1 second. This whole thing is equals to WL square over P times 1 over KL square, and then okay, we have the KL there, so it should be just 1 KL, right? Only 1 KL, thank you. Okay. Oops. Let me clean this green thing out. Okay. So we can solve for DRA and DMA. W terms ought to be known, right? W is known, is given. So for MA and RA, well. Let me do it this way. I will put the sign in there. And then, well. RA would supposed to be the same. It will not be changed with the effects from the axial load. No, we will be able to solve for that, but okay, not now. We push this activity on Excel at the latter part of this class. So we'll be writing that down. The M A over P. Now we have everything over P, right? We can simplify, make MA over P is equal to RAL over P eta, and then minus WL square over P omega and you see that the P is, well, could be cancelled out. That's the first equation. And how about, wait a minute, I got to divide by the C. Okay, that's the first one. The second one, MA over P is equals to minus and minus, okay, minus RAL over P alpha over beta and minus WL square over P delta over beta P is gone. So it's up to us. We can clean things out a little bit further. Well. Alpha over beta minus eta over C. That multiplies by the A. And on the other side, we get the WL omega over c minus delta over beta. And that makes the RA. Why did I write it? RA equals to WL multiplied by this over this term well, this was supposed to be 0.5. RA will be 0.5 WL, but we got to check. We got to check. It just don't conclude and summarize this without seeing the real result. So M will be calculated from our RA. So either this equation or this equation. So basically, if you stuff in the RA back into this expression in the circles, so your MA will be WL square, right? You can see you have WL square, and here RA is a WL multiplied by L. You get WL square. So WL square multiplied by some function, of course. Well, this function was supposed to be something like 1 over 12 if the p approaches 0. But if we want to express this function in terms of something, we call it the magnification factor. So it gives you the sense of how much the moment is magnified by the effects from the second order deformation. We instead write this function in this term. So you pull out the 12 from that function. Okay, pull out the denominator 12. So basically what you used to have in that function, you multiply by 12, and then you get the magnification sense. Like it should start from 1.0, and then if you have the magnification, you have the increase, then this 1.0 will just ramp up, right? If it gives you the decrease of the moment, then it's gonna come down. So what we will have on the Excel is going to be the plot between P over PE ratio and, well, this whole function. Where should I will not write this 12 like this. Just understand that F will be absorbed in there already. Call it magnification factor. So supposedly this will be at 1.0. And then later on it's gonna gear up something like that. The difficult thing for the writing on the iPad is the control on the paper seems to be okay. Right, so let's plot this thing. Here I just showed you the case where your beam is subjected to the axial compression. You do the axial tension for yourself. Okay, that is, well, aka homework. Alright, not difficult at all. I bring you to this far already. Maybe another case where you have the beam under the presence of the distributed load that looks like the triangle, so that varies linearly with the distance x. And this is the W. The magnitude W is there. The length is L. The EI is there. X equals to 0. The X equals to L. Apply the reactions, apply the axial force, apply the moment, So for this problem, you can estimate that we will end up with something with the higher order terms. What is that? It will be even higher than the problem we worked on before. So So how much is this? This is equals to x over L multiplied by W. So in your equation, we need to again fix the particular solution for this case, because it's gonna include some higher order term than last time. So MQ the R, everything we stick with the sign we had before. Sigma moment is equal to 0 at point Q clockwise, right? MQ. If you want, I think it is more fun to come back, not making it the same way as before. So MQ is the minus sign minus P times Y plus MA minus RAX, and then the effects from that ramp load. So we have plus that distributed load plus WX over L multiplied by X over 2. So you get the area of the triangle. The height, which is WX over L multiplied by the base, which is X over L. You get the area of the triangle, and then you multiply by the moment arm. What is the moment arm? X over 3. Basically, it is nothing but just a change in the mathematical formulations. You move over through this. There's nothing special, no new concept. Everything's still the same. RAX, move it to the other side. RAX minus MA minus WX cube over 6. So on the left hand side we have the minus MQ minus PY. The MQ is the EI times that curvature, which is
negative, so we neutralize it. Minus p times your y is also negative. We need to neutralize it, and that's exactly the same for the right hand side. And that is the second derivative of y, x plus k square y r a x over e I minus m a over e I minus w x cubed over 6 l e I. So we just have more fun. I will not list the homogeneous solution there. I will continue with the particular solution, and we need the cx cubed plus dx squared plus ex plus f. So it's just going to, well, be more laborious than before, but still we are capable of fixing this. Differentiate this particular solution twice. We have c3cx squared and another time 6c x, right? Plus 2d. Ex gone, f's gone, plus the k squared, which is p over ei, and this whole thing equal to this term on the right hand side. So we equate the term cube term first. Cp over ei is equal to minus w over 6 LEI and that makes your C equal to minus W over 6 PL now. The C term, we fix it. Next, look at the D term. The D term multiplied by x squared. You don't find any x squared on the right hand side, so clearly the D has to be 0. There's nothing to do with the x squared there. Next one, we have the 6cx plus the pex over ei equals to rax over ei. Okay, the linear term of the x a over ei. 6C 6C plus P over EI times E P over EI times E, okay, X term, and I will substitute the C term there. Oops. So 6 multiplied by C, that makes her minus W over PL. Push it to the right hand side to figure out. Plus W over PL. And then to get the EI will be gone. This EI is gone. That's gonna make another EI there. The P will be coming down, square and L, just like this. And then how about the F term? The F term to D plus PF over EI equal to minus MA over EI. But you know that the D is 0. EI cancel out. So we have the F equals to minus MA over P. Alright. So our Y particular solution alone is equal to minus WX cubed over 6PL. We don't have the D term, we have the E term, so plus RA over P plus W WL over over P multiplied by 1 over KL square times X and minus M minus MA over P. I over P W that is 1 over k square. K square, you need another L. Okay, KL square, then you get the WL over here remaining P. Okay, let me just copy this to the next page. So y of x is equal to a sine kx plus b cosine kx plus this term and this one. Done. Okay, so let's figure out. We enforce the boundary condition. Maybe I provide this dy dx equals to ak cosine kx minus bk sine kx minus w3 wx squared over 2pl plus a over p plus, is that the real plus? Okay, plus the WL over P 1 over KL square. Alright. AK cosine minus BK sine. Differentiate, you get 3WX square. 3 cancel out, you get 2 over 2PL. X differentiate RA over P WL over PKL square. Okay. So start with Y at 0 equals to 0. Zero plus b minus ma over p. So that makes the b equals to ma over p. Right, substitute out 0 0. Second, dy dx x equals to 0. Is equals to 0. So I get the AK minus 0 plus RA over P plus WL over P 1 over KL square so A is equal to minus RA over PK minus WL square over P times 1 over KL cube. The A this time is big, huh? Last time what was the A? Huh? Really? Okay. Okay. Right. Number 3. YL is equal to 0. Just 9 o'clock. Well, still a long way. YL equals to 0. Oh, we got to run out of this room at 10. Okay, so 9:55 we got to stop. So what? So what? So what? So what? You get the A. Multiply by sine KL, and your B plus M over P. The straight line isn't a straight line. Well, okay. M over P. Let's check the M over P we had before. Yeah, okay. MA over P cosine KL, and then the other terms. So let me just copy them and paste here. And don't forget that we have to replace the X by the L. Alright. So start with RAL over P. We have 1 RAL over P. We have the second RAL over P, which is sine KL divided by KL. Okay. And then the next term plus MA over P. Cosine KL minus 1. That's it? Okay. And next we need WL square over P term. WL square over P length scale multiply by WL square over P. Okay. First, WL 1 over KL square. The second one minus WL square over P 1/6. The third one minus WL square over P as well, sine KL over KL cube. Okay. Quite a morning exercise. For this time, the RA will be affected by the axial force. There is not symmetry like before. RA will be changed. Alpha, beta, delta. So MA over P is equal to minus RAL over P alpha over beta minus WL square over P delta over beta. Okay. So move to equation number 4. Substitute AK. Condition number 4. dy dx at L equals to 0. So we take the A, multiply by the K cosine KL minus the B, which is MA over P K sine KL and then this term just copy and paste and change X to L because we substitute, and that's it. And we move forward. Start with the RAL over P. We have 1. We have minus cosine KL. That is the RAL over P terms. Next, plus the M A over P. We have the KL, put the minus in there, minus KL sine KL. Alright. Two terms in there, M one term in there, W 1, 2, 3. So plus WL square over P. WL square over P. First one over KL square, and then the second one minus a half WL square over P, and the third one minus cosine KL divided by KL square. Minus WL square over P. Factor that out. We have KL cancel out. You get KL square only. Cosine KL over there. Okay. Ready to solve? What did we use later before? C eta omega. C eta omega. Alright, so this equation will be copied and paste here, and we will set up moment minus RAL over P C over eta minus WL square over P omega over eta. Okay, and we will get the MA. And that's just the MA. Okay, so you have the magnification or reduction factor. Okay, it could be something. Okay, for MA, and for MB it will be another factor. Likewise for the RA and RB will be affected. So yeah, we can move over to Microsoft Excel. Is there anything? We write MA. Okay. Oh, okay. Over here we write MA. Previously we wrote. Okay. All right. Let's fix a little bit. So the A multiplied by C over eta minus alpha over beta is equals to WL square multiplied by delta over beta minus omega over eta and again the RA is going to be equals to, no, not the WL square, it is just the WL. We cancel out. So equal to one term divided by another. Okay, then you substitute later.
So we will start with the first part that we derive for the beam under the uniformly distributed load. We want to find the RA, right? RA equal to something and something. Fine. We just get the KL. So sorry. Let me pull this up on the screen. You got it on the screen? Okay. I think it is coming up. Okay. P over PE KL. So what is the relationship between P over PE and KL? Something. Let's just find the alpha. Alpha KL is 0.01. Just put like this first. So what is the relationship between KL and POPE? I don't remember. Huh? What? Pi square what? Pi square. I will put the KOPE ratio here and then compute the KL. If I don't remember, then just rederive. P over PE, which is pi square EI over L square. This is the K square, right? L square over pi square. Okay, that is this. So P over PE ratio, in order to get the KL value, you get the P over PE multiplied by pi square, and the KL is the square root of this thing, and take P over PE, right? Oh, sorry, you don't see anything there. Okay. So KL is equal to pi, right? Multiplied by the square root of P over PE. Alpha. So let's check alpha. For the uniformly distributed load case, alpha is equals to 1 minus sine of KL divided by KL. We get the alpha. You need the beta as well. The beta is equals to cosine KL minus 1. And then what? Delta equals to 1 over KL square minus 0.5 minus cosine of KL divided by KL square and then the next one we need the eta, which is actually 1 minus cosine KL. Actually it's the same as something beta. 1 minus cosine. Oh, okay, yeah. And then the what? Theta, C, okay. C minus KL multiply by sine KL. No. And omega is equal to sine KL divided by KL minus 1. Oh. Sine KL divided by KL minus 1. Okay. So, for the scale for the RA, we have the omega divided by C minus delta divided by beta, and then divide this whole thing by alpha divided by beta minus eta divided by C, right? 0.5. Okay, we are good. 0.025, 0.05. Let's just copy down. We will be just up to 4.0. Do you want it to be a little bigger? Okay. Yeah, right, you see 0.5, no matter how much the P is, this is always constant because of the symmetry. And we've got well, this is the F for RA. Let's see the scaling for the moment. So the moment will be given by moment is equal to minus RAL. We can take the L out, right? So take the minus the factor from the RA. Okay, WL square will be taken off. Multiply by eta. Okay, divide by theta. Divide by C. Okay. And then minus WL square. Okay, we factor this out as well. Omega divided by C. Alright, 0.83. Well, if you know 1 over 12 is what? 0.08333333, right? Basically, we miss the minus the 12. If we want the modification factor from WL square over 12, then you multiply by this 12, you get this. And okay, magnification factor is there. Let's see if we compute this from another equation which is available, which is the minus RAL multiplied by alpha over beta, etc., etc. Okay, so we have 12 multiplied by minus RA, and then multiply by alpha divided by beta, and then minus the delta divided by beta. Okay, identical. Supposed to be. We shouldn't go against the mathematics. So we will plot between we hide Okay, this looks terrible. Okay, we insert the plot. So you can see something like this. Let me adjust. This magnification factor goes to 100. That will be crazy. So about 3. Around here it's not continuous. So we get some sort of 1/0 happening because of the formulation we have. If you want to smooth it up, just go check this value using L'Hopital's rule. But the one divide by quite close to 0, and then it wasn't evaluated properly, happened that place. So okay, the number increased. I just gave you the side for the compression, so you figure out another side which is for tension. All right, that's the first thing. The second thing, as you have the M and you have the RA, right, both M and R, that means you now can complete the deformed shape equation y of x. So, and you have y of x, everything was determined, R was determined, M was determined. You'll be able to get the deformed shape under a given W value. So you keep the W value a constant, just W. All right, you don't need to vary the W, but you will need to vary the PO/PE ratio. So when you plot, the x-axis was supposed to be the normalized value of the x over L. Okay, plot the x over L ratio in the x-axis from 0 to 1. For the y-axis, that will represent your deformed shape, but you shouldn't go with the just y, because you're gonna get the factor like the W and etc. etc. Basically, you can determine the maximum deflection at the midspan of this fixed without the axial force, right? Fixed support the beam under the uniform load. I think the delta is it 5/384? You can just go find it out, or you can just run analysis and find out that value. So when you plot the scale, okay, like the magnification of the case where you have the axial force being 0. So for that case, you have the deflection at the mid span being 1.0 without axial force. So you're going to have the deformed profile, but you normalize the deformed profile by the maximum deflection at the midspan. So y-axis turns out to be the normalized deflection, and the x-axis is a normalized length or normalized x value. Okay, maximum 1 and 1. Now, under the presence of compression, we're gonna use the PO/PE ratio like before in the former homeworks. So I gave you like 4, 5 PO/PE ratio. I don't remember that. You just use those numbers. So under compression, then at the midspan, you will not get just 1.0. You will get more than 1.0 because you magnify the deflection by the compression. Whereas for the tension cases, you have less than 1.0 because the axial force, axial tension helps stabilize your structure and reduce the second order from the tension, reduce the deflection. Okay, so let me give you a quick summary. You have to derive the tension case, axial tension case. You come up with the table like this, and then you plot the deformed shape for both compression and tension. Alright, same thing. Okay, use Octave, try to put it up, plot it there, use the program, get used to it. I can share this. So this will be upload if nothing goes wrong with the video. Next we have another case, right? Case where we have the distributed load which is not uniform, triangular. This is the uniformly distributed load. For this case, we need to redefine all those unhigh. Redefine all those values. So let's check alpha for the next case. Alpha is 1 over sine KL over KL. Whoa, not change. How about beta? Cosine minus 1. Oh, seriously? So delta 1 over that thing, and then minus 1 over 6. And then sine over KL cube. Oh, so cosine turns out to be sine. Sine KL over KL cube. Okay, and then eta. Yeah. Delta 1 over KL square. Thank you. But 1 over, is it the KL square already? Right? 1 over KL square minus 1 over 6. So this is okay already. Okay. Let's move to eta. Why eta? Wait. Previously was C before eta. Now, oh, okay. I switched the eta and the C, right? So, okay. So, oh, that just eta. This one is C, right? Eta C is equals to 1 minus cosine. Eta is minus KL sine, and then the omega is okay, a little bit more complicated. Got to change everything. It is 1 over KL square minus 0.5 minus cosine this divided by KL square. Okay, and get the omega, and then we need to get the R. So that is the, just clean up, delta over beta minus omega over eta divided by C over eta minus alpha over beta. Okay, that's the R. How about the moment? Moment is equal to one second. Okay, RAL minus R, right? Minus R multiplied by alpha divided by beta, and then minus W square, okay, delta divided by beta. Okay. All right. We don't use this one for now. We hide it, and then double click. Well, first of all, let's look at this one. The parameter we are plotting over here. This is on the left support where the load start from 0 intensity. That side, if we consider the case where the axial force is 0, it is the 1 over 30 multiplied by the WL, right? So if I want to get magnification factor, I just multiply 30 back in there because we took out the WL square already. Then we also take out the 1 over 30 and then you multiply by 30 up here. So 30 multiplied by this factor. Okay, it magnifies as well. Now you find the R, you find the M already. You can take moment on the other side. Okay, so if you take moment, you have reactions multiplied by length. Reaction is there already given in this column. You have the moment at the end, starting end, okay, already. You will have the triangular load, which is W times L square over 6. That you incorporate that apply moment, and that's all, right? In order to come up with the MB, all right? And then when you get all of that done, then the MB is generally it is WL square over 20 if P is 0. So you will take the expression for MB multiply by 20. You will get magnification factor for MB. And that start from 1 and then it will vary. So prepare this. Then you get all RA and MA. You have Y given in terms of W, RA and MA. RA and MA are written in terms of WL square, right? So everything will be expressed in terms of W, L, EI and KL. All right. So you'll be able to plot the deformed shape again for compression and for tension, but this is for the linearly varying distributed load. So your homework includes 2 parts: uniformly distributed load and linearly varying load. Show the deformed shape under different PO/PE ratios. Get the tension case derived for yourself, right? And that will be it for this homework. Due. Oh, you're lucky, right? Because Thursday we don't have class. Well, that's gonna make the Monday class the due date. All right, we don't have Thursday class. Well, actually, if you work on this afternoon, then you get it done already. You don't need to wait until the next week. If I say that you got to turn this in tomorrow, I will get it tomorrow. Time management, actually, it's up to you. Okay, tomorrow we will have a class over here, this room. I'm gonna show you the programming for the frame structure, 2D planar frame. So start at 7:30 as well. All right. If we can make good progress tomorrow, we might be able to wrap up the planar frame structural analysis program. So let's see, because we can move faster than before. Hopefully you can wrap it up. If we cannot, then we do it another time until we get it all done, wrapped up. All right. This class, is there any more question, comments, anything? It seems to be good now. Okay, all right, then see you next time tomorrow.